is written.
Professore, scusi,
Sì?
senta, una domanda sulla recitazione 1, ma
Sì?
per quanto riguarda la compensazione dovuta, diciamo, alla temperatura, diciamo, cioè, dobbiamo considerarlo oppure perché lei, diciamo, nel video fa vedere che più o meno la temperatura rimane sempre intorno ai 22-23 gradi
Ah.
e quindi noi cioè, possiamo fare l'ipotesi che comunque rimane, cioè non influenzi la misurazione oppure dobbiamo tenerne conto in qualche maniera?
Okay. So your colleague is asking about laboratory activity number 1 and specifically the temperature compensation. And the question is about, do you have to take into account this temperature compensation or not? The answer is it depends on you because it depends on the operating temperature. I'll give you the information on that during the test. So if you feel that the temperature compensation is negligible with respect to the measurement, there is no need, of course, to take a computation time for the laboratory activity. On the contrary, if the temperature compensation could be of importance for your measurement, then it is required to take that because otherwise errors will be too high. Okay, so the discussion is upon you. How much the temperature compensation will be. Therefore, is worth to take into account, it's worth to take into account this temperature compensation. Just to give you an example, if your operative temperature is giving you a temperature, a strain, a compensating strain of about, let's say, 5 microstrain, okay, and your measurement is about 500 microstrain, so maybe you are in a measurement range that your temperature compensation is not that important. On the contrary, if you are having the same operating temperature, so the same strain compensation, but your measurement is about 5 microstrain, so you have your temperature compensation that is equal to your measurement, and therefore maybe that is the reason why you have to take into account that temperature compensation. Okay, so same operating temperature, same strain gauge, but different effects. Have I asked the question?
Sì, sì, perfetto, grazie professore.
Prego. Okay, I think that we can restart our class. We saw the estimating method based on a multi-degree of freedom system, the frequency domain. Now let's see a different method that is based on a multi-degree of freedom system, but it is operating on in a time domain. Okay. By the way, because these methods are having a number of unknowns that are generally much less than the number of equations, okay, these methods are referred to the curve fitting methods for the estimate of the model parameters. Okay, so let me write that now. Generally, the number of unknowns are less than the number of equations. Just to give you an idea, the number of nodes are, let's say, 5 modes, for example, 5 modes, 10 modes. That is a very large number of mode shapes that we are going to measure. The modes are defined, let's say, in 10, 20 degrees of freedom. So the number of unknowns would be of order of magnitude, let's say, 100, okay, including residual terms, including mode shapes, including natural frequencies, including damping ratios, okay, for a very large number of degrees of freedom, whereas the number of equations, okay, are about 2 to 12, 2 to 13, to 15, to 15, okay, so 4,000, 8,000, 16,000, 32,000, and so on equation. So that's the reason why we are referring to these as curve fitting methods, okay? Use the model parameters. Okay, and the one that we already saw that is operating the frequency domain is just one of them. Now let's see what's happening in the time domain. Okay, so the method that now I'm going to introduce you is the complex exponential method. Okay. And this method is a time multi-degree of freedom system based method in time domain. Lots of variants exist. We are just seeing you one of them, the basic one. The main advantage is that it does not require any initial guess, and that is very important. Okay, and it uses the impulse response function as a function to be considered, because instead of using the frequency response function, it operates, because it is operating in the time domain, it uses the impulse response function. Okay, impulse response function. Okay, please remember your, just from the basics point of view, just to remark you, your frequency response function of omega, okay, was set equal to a fraction series expansion from R that goes from 1 to n, and is the number of modes that are available in our analysis, residual terms, divided by your omega n r theta r plus j omega negative omega n r to square 1 negative theta r square, remember, okay, plus its complex and conjugate, so from r that goes from 1 to n once again, okay, in which, or maybe we can just remove and be consistent. Okay, AIJR complex conjugate divided by omega n r theta r, okay, plus j omega plus omega n r root square 1 negative theta r square, okay, all together, of course. Or in a more compact form, we can rewrite that as a summation from the index that goes from 1 to 2n, numerator the residual term, denominator typical one, so omega n r theta r, okay, plus j plus j omega negative omega t k, okay, the dumb natural frequency, in which the dumb natural frequency or index, whatever index r, is omega n r root square 1 negative theta r square, okay, and omega t r plus n is negative your omega r, plus n is the complex and conjugate of the corresponding one, okay. Okay, the impulse response function, the corresponding impulse response function, could be rewritten as the corresponding impulse response function is, as you well know, hij of time, that is equal to summation sign from the indices that goes to up to 2n, aijr, the residual part, time, the exponential, the complex exponential, so lambda r t, okay, in which, remember, lambda r is the pole of your system, negative omega n r theta r plus j omega r, the damp natural frequency. Okay, so generally what we are having is the FRF, okay, because we already know that from your measurement that is your starting point. So the impulse response function is obtained just by inverse Fourier transforming your FRF, okay. So generally your h of omega is known, for example, from H1 or H2 or whatever estimator, okay. Thus, the impulse response function, the IRF, okay, is obtained just going back in time domain through the inverse Fourier transform. Okay, the h of omega. Okay, so your h of t is the inverse fast Fourier transform, because generally we are using the fast Fourier algorithm of your h of omega. I am neglecting the indexes because we are referring to consistent quantity, time, and the frequency. Okay, so because of this, the impulse response function is then available, okay, at a equally spaced time instance, okay, and this interval delta t, of course, is equal to 1 over your frequency resolution, delta f, okay, so that we can write this. So that is our starting point. Whatever hij of the first time, okay, it is your first item that you know. Then you got hij of the first time, the second time, okay. Then we got hij of 2 delta t, okay, up to whatever number hij of q delta t, okay. And these quantities are known, okay, because we are inverse Fourier transforming, so we are going back into the time domain, starting with the information that is ready available from the measurements, that is your frequency response function. Okay, now in order to ease the notation, I am dropping all the indexes corresponding to the degrees of freedom, the pair ij. Okay, so I am calling hij0 as your h0. I am calling the hij delta t is as h1, h2, up to the end, that is h2. Okay. Moreover, in order to reduce as much as possible the notation, okay, I am simplifying the terms of the residuals. So the terms ij of the residual term r, okay, I am writing that as your AR, and the exponential part, that is E lambda R T, or delta T, sorry, delta T, it will become your VR, okay? So, as a matter of fact, my HR in this simplified notation that represents your impulse response function at whatever couple ij evaluated at time TL equal to L times your delta T, okay, and that is equal to the summation sign of indexes goes from 1 to the 2n, that is the number of modes available there, AIJR, okay, E2 lambda RTL will be rewritten as summation sign from R goes to 1 to 2n, and then AR VR of index L. Okay, and of course this index L goes from 1, 2, up to the number of sampling points, okay? And S is the number of sampling points in the time domain, of course. And generally speaking, you can say that this number of sampling points is much larger than the dimension of your system. The same discussions that we had before. This number equation is very, very large compared to the number of unknowns. Okay. Now, I think that it is quite clear. If not, please tell me what are your doubts. And because now I'm focusing on this very last equation, that is a simplified notation. Okay, so let's consider that equation. Okay, and then I explicit that equation. So I can write that as H0, okay, that is equal to A1 plus A2 plus A3, whatever, plus up to the last term, okay, A to N. Then I'm writing the second term, H1, that is equal to B1, A1 plus B2, A2 plus B3, A3, and all other contribution, okay, until B to N, A to N. Then I can write the second H, that is H2, is equal to V1 square H1 plus V2 square A2 plus V3 square A3 plus all the terms until the last one, V2 until the whatever index, let me call it HQ. So HQ is equal to B1 to the power of Q, A1 plus B2 to the power of Q, A2 plus B3 power of Q, A3 plus everything until the last term, 2n to the power of Q, A to N. Okay. So once we define these support variable AR and DR in the way that we define them, the impulse response functions for each time sample L could be rewritten in this way. Now, I'm asking you to fasten your seatbelt because now I'm just playing with a little bit of algebra, okay? So please consider that our goal, going back a little bit, is the estimate of model parameters. That is, we would like to estimate the residual terms, AR, the poles of the system, lambda R, that is VR, and by the way, we don't know in the considered frequency range the number of modes that are there. So we consider also that the number n is our unknown because we don't know what is the number of modes that are representing your system dynamics in the considered frequency range. Okay, so let me write there the unknowns are once again, okay, your residual terms, your poles, and the system order, and because we don't know, okay. So in order to find out this approach, these unknowns, let me play with a little algebra. So let's multiply, okay, the previous system by some coefficients. these coefficients are beta I. We don't know what they are representing right now, but just let's assume that these are coefficients, beta I. I is, of course, the index of my time sampling, okay? So by multiplying this equation, it means that we have to multiply both sides first, and left-hand side and right-hand side terms of this system of equations. So what we got here is beta 0 times H0, that is equal to beta 0 times, A1 plus beta 0 times A2 plus up to the very end, beta O. Beta 0 times A to 2n. Then we got the second equation, beta 1 H1, that is only equal to beta 1 B1 A1 plus beta 1 V2 A2 plus all the other terms until the very first one, V2n A2n. Okay, then the second term.
Excuse me, Professor. I
Yes.
didn't understand what is this beta I value. Is it a random value?
No, it's not a random. It's a prescribed value. It's a coefficient, a set of coefficients. Okay, so beta I are some coefficient that I'm using in your previous equations, set of equations, as you can see right now. Okay, I'm going back to these values once I go on with the approach. Okay, by now just consider that I'm introducing additional coefficients, beta I. Okay.
Okay, but I have one more question.
Uh-huh.
Beta I stay unknown for us, or we just give them some?
These are unknowns, but let's assume that these betas are there. That is why I'm asking you, I ask you to fasten your seatbelt. By now, just assume that someone gave you these beta I's, okay? And see how we can use them. Okay, our first usage is to use these beta I's to multiply each equation by the corresponding time step. Okay, beta 0, beta 1, beta 2 as I'm running. Okay, just hold on for a very few minutes. Okay, so let me go ahead. So beta 2, B1 square, A1 plus beta 2, B2 square, A2 plus beta 2 B2n square A2n, and then going down until the last term that we are considering, beta q times HQ equal to beta q B1 to the power of q A1 plus BQ B2 to the power of q, okay, A2 until the last one, plus beta q B2n power of q A2n. Okay. So what I have now is, let's say, an equivalent set of equations as we have before, but we introduce these coefficients beta I. Now, let me sum up all the equations. Okay, so by summing up, the previous equation, what we got is this one. So I'm summing up all the left-hand side. So from the index, it goes from L equal to 0 up to Q. Then we have beta L times HL, and that is your left-hand side, as you can see. Then I have to add up all your right-hand side. But before doing that, I am summing up by going horizontally, okay? So that is equal, okay, to sum from L that goes from 0 to Q, beta L, and then I'm summing up everything. So summation from R that goes from 1 to 2n, AR, BR to the power of L. Okay. Please consider that this could be rewritten in taking into account that on the right hand side, the two summation indexes are independent one each other, and therefore we can rewrite this equation as summation from L that goes from 0 to Q BL HL, that is equal to summation from R that goes from 1 to 2n, and then the AR summation L goes from 0 to Q beta L VRL. Okay, so that is this equation that is in a sense is equivalent to the previous equation, set of equation, that is in turn equivalent to the very first system of equation that we got. Of course, we are assuming that someone is telling me who are these coefficients beta, okay? But how can we use this information? So in a way, we are parameterizing our set of equations by using the indexes, or the coefficients, sorry, beta. But what are these beta L? Okay, so how can we introduce this beta L so that our estimating process could be, let's say, could go straight to our goal, that is identification of your model parameters? We can have whatever choice, but if your coefficient L, beta L, are the coefficients of the equation that is this one, 0 to Q beta L VRL equal to 0, then maybe we have some advantages of that. Okay, so once again, we have introduced the coefficients beta. That could be whatever, okay? And because of that, we end up to that equation that you can see now on the screen between your rectangular, okay? So now, if we are assuming that your coefficients beta are the coefficients of that equation, maybe we can have some advantages, and indeed we will have. Now I'm showing why. By the way, if that is true, so if the beta L's are the coefficient of that equation, then we can rewrite that equation as beta 0 plus beta 1 BR plus beta 2 BR square plus to the very end beta Q BR to the power of Q, and that is equal to 0. What we got is a very nice equation. Why? Because we are having an algebraic equation of degree Q, okay, having thus two solutions, okay, two solutions of VR, okay, but we are very happy, aren't we? Can you see the reason why we are very happy? Is someone of you seeing that we are happy or not?
I think because the number of unknown and our equation are the same.
No, the reason why we are very happy, and indeed you should offer some afternoon drinks to all your colleagues, is that if betas are such a coefficients, the solution of the corresponding algebraic equation is just one unknown, because we are having the VR that are our solutions. Remember, the VR, going back a little bit, here, the solution, the unknowns are VR, and VR is having, where is it? The poles of the system. You remember, VR is exponential e to lambda r delta t. Okay, so by introducing these coefficients beta, okay, and by assuming that these betas are the coefficients of that equation, by solving the roots of the algebraic equation like that, then we have one of our solutions. Then we are having the VR, okay? Now, let's see how we can have these betas now, because we don't know yet what are these beta, okay? But if they are the coefficients of that equation, then it is just a matter of whatever numerical subroutine to find the roots of whatever polynomial of degree q, okay? So in order to give an idea, let's us
Excuse me, Professor.
Yes?
Out of 9 solutions, how can we assume the right solution of VR?
Say it again, please. How can?
We will be having 9 solutions for VR, right?
Yes.
Then which one is the correct one? How can we decide?
Yes, you're right. That is a question. I'm going to answer to that question later on at the very end. Okay?
Okay,
Your question is good. So you are saying that you have Q solutions, okay? Q solutions for the VR. So the question is, who is telling me which is the right solution? Are all solutions good, or just one is good? We don't know yet. We can answer to that at the very end, okay? And in order to answer that, let me now assume that your Q is equal to 2n. But once again, we don't know anything about the number of moles that are in your frequency range of interest. So we don't know yet also what is this number n. But let's assume that we know that as we did for the solutions, okay? We will answer that to the very end, okay? So remember, n is the number, okay, of degrees of freedom in the modal domain of the system, okay? Okay. And remember, the solutions are complex and conjugates, okay? So let's assume that we know this number. So let's assume that Q is equal to n. So when referring to the previous equation, okay, when referring to, if that is true, when referring to recalling that the summation from L equal to 0 to Q B L B R L is equal to 0, okay, then because our hypothesis that Q is equal to N, okay, we can have that your final equation, okay, will be equal to summation from L that goes to 0 to Q that is equal to L this time, beta R mu R L, okay, equal to 0 for each value of the index R, okay, 1, 2, up to 2n. Okay, but if that equation is true, remember we assume beta, so that is true, okay, then going back to the initial one, what we can say is that your from let me write it this way, from equation, let me call it star, that is this one here. Okay, so from equation star, we can write that summation from L that goes from 0 to Q equal to L beta L H L equal to summation from R that goes from 1 to N A R summation that goes from L E0 to Q equal to N beta L B R L. Okay, and because of our hypothesis, okay, this term is 0, okay, and therefore that is 0. So what we got in turn, we got that according to our choice of the coefficients beta, we are also having that your left-hand side, that is a summation sign from 0, from index L, going from 0 to Q equal to N beta L H L is also 0. Now, I'm doing whatever with the coefficients beta. So let me assume that if beta 2n is equal to 1, I'm assuming that because I need it, okay? Then we can rewrite that equation as summation from L equal to 0 to 2n negative 1 of beta L H L equal to negative H to N. Is that correct? Because of my choice, okay? I can rewrite that equation as H0, H1, up to the last one, H2N negative 1, okay, times beta 0, beta 1, up to the last one, beta 2n negative 1. Okay, and that is equal to negative H2n. Okay. Now, because we have just obtained this very nice equation, I can think that we can restart my procedure, okay, that starts from the very, very beginning. That is, let's assume that we are starting from this very initial point. So I'm going back, I'm going back, I'm going back. I hope that you can see scrolling up my screen. Okay, going back here. Okay, and let me call this step A. Okay, and then I'm repeating all the discussion that I had so far from that point, from that step A to this very end, that is here, step B. Okay, so by repeating the approach from A to B, okay, but using different time samplings, okay, in the impulse response function, okay, we have the same results, okay? I'm not going to that right now. So just by, let's say, shifting one time shift with respect to the previous one, what we can say is that we are ending up to H1, H2, H shifting of one the H index. The coefficients are always the same in number and are always the same as the indexes. So beta 0, beta 1, up to beta 2 and negative 1. Okay. This time, the known term is negative H2n plus 1. I shift 1 after that. So I can redo that many times, okay? And therefore, I can build this equation, okay, which we are having H0, H1, up to the last one, 2, and negative 1. That is the first equation that we got. Then I'm writing the second equation, H2, H1, sorry, H2, up to H2n. Then I'm going down, repeat from A to B many times until I reach this index, H2n negative 1, H2n, up to the very end, H4n negative 2. That is multiplying your unknown coefficient, beta 0, beta 1, up to the last one, 2, and negative 1. And that is equal to negative this H2n, H2n negative 1, up to the last one, H4n negative 1. Okay, please note the coefficients that are in the square parentheses, that is the matrix of H, is a matrix of known quantity because they are representing the impulse response functions at different time instants that are all knowns because we had information of the FRF. And remember, we made the inverse Fourier transform of the FRF in order to have these H coefficients. Also, the right-hand side, that is the vector of the known terms, are known because all the coefficients are the same impulse response functions that are already available once we know the FRF. So the only unknowns in this equation are just the coefficients beta. And then we are all set. Then we are very happy. We can party all the night long because we have a way of evaluating these unknown coefficients. Indeed, if we rewrite this equation by introducing this matrix of coefficient lower h, okay, we introduce the vectors of unknowns, beta, and we introduce the constant term, the forcing term, if you want, h tilde. Remember, the dimensions are 2n times 2n for the matrix of coefficient h. The unknowns coefficients are 2n times 1. And of course, the tilde h is 2n times 1. Okay. Then we can rewrite the previous equation as h beta is equal to negative h tilde. Okay. And thus, what we can have is that your unknown coefficients beta could be obtained just by taking this matrix operation h to the inverse, then times h tilde. Okay. We are all set because now we are ready to estimate your model parameters. Remember, Here we are. Those unknown coefficients, betas. And by assuming that those coefficients are, where are these? Okay, are the coefficients of that equation, we end up to this very, very nice system here that could be solved for these coefficients, beta. So at this point, we know what are these coefficients. Then we are all set, because then first, by using beta that we'll just solve, okay, VR are solved by finding the roots of this algebraic equation. Remember, beta 0 plus beta 1b plus beta 2b squared plus up to the last one, 2n b to 2n equal to 0. Okay, once we got the roots of this polynomial, then we have the VR, and therefore, because your VR that we have just found it out is equal e to lambda r delta t, we are estimating your poles. That is your first identification. Okay, now we know the poles, that is, we know the VR. So residuals term, so residuals are obtained from this equation. Remember, just the very starting point, HL is equal to summation sign from R that goes from 1 to 2n, AR, BR, L. If you want, that is equal to this equation, 1, 1, 1, V1, V2, V2n, V1 square, V2 square, V2n square, up to the last one, V1, 2n negative 1, V2, 2n negative 1, up to the last one, V2n, 2n negative 1. That is multiplying the vector of the unknown residuals, A2n, and that is equal to H0, H1, up to the last one, 2n negative 1. So that we can rewrite that equation by naming, this matrix as the matrix D. Okay, this is the vector of unknowns A, and this is the known terms H once again. Okay, so what we got here is B times A equal to H, the same system as before, and thus what we got is the estimate of the residual terms is given you by B to the minus 1 times H. Okay, and therefore we have also available your residual terms. Okay, so we got the poles, that is your natural frequencies and damping ratio from the VR. Once we know the VR, we can have the residual terms A, just by solving that equation. And therefore, you are done. There is just one open question, that is, who is giving me the information of the model order? That is, how about N? Because remember, we assume that we know N. And once we know N, we are using it. And when solving the polynomial, the roots of the polynomial here, okay, who is telling me what's the good VR? Okay, as your colleague pointed out. And once again, who is telling me who is N? So I know that I am rude with you because I'm not giving you the right answer right now, and I kindly ask you to wipe your tears that I know that are coming out from your eyes, but please wait me until Friday, because Friday I'll give you the solution to this very, very sad problem of identifying n. I know we could have a party tonight, but please refrain until this Friday. 2 days are not that much, so please hold on. We are going to have the answer to this question, and therefore we will see how we can use this complex exponential method for estimating your model parameters. So that's it for today. Questions, please let me know now. Okay, if there are no questions, thank you very much. See you this Friday. Okay?
Thank you, Professor.
Thank you, bye.